So our next speaker, Dr. Scott Peltier, will on stage. He is a research scientist at the University of Michigan, and his work centers on functional MRI data acquisition and analysis. So in today's talk, titled Harmonizing Functional MRI with Open Source Data Acquisition and Reconstruction, Dr. Peltier will discuss open source fMRI approaches and describe a fully vendor-agnostic portable fMRI protocol that ensures identical sequence execution and image reconstruction across different scanners and software versions. That sounds so cool.
Thank you very much. All right, I'd like to thank the organizers, thank HBM, and acknowledge before I even start that the leader of open source agnostic sequence programming at Michigan is John Friedrich Nielsen, who's not here, so you get me. All right. No disclosures. All right, so we're here in some capacity because we like to do MRI, fMRI, right? We're studying biology, we're using our preferred modality, in this case, MRI, and then we're gonna do our fantastic analyses, maybe AI as the last speaker we'll talk about. But because this is a measurement, experimental science, we know that at each step along the way, we have potential for variance creeping in to the process. So what I'm focusing on today is that variance that we're getting kind of at the site acquisition level. So we know that designing our sequence and running it, collecting any calibration scans that we need to get, generating our case-based data, then doing the reconstruction and any on-scanner pre-processing that we're doing, each of those steps might put in variance that we'd rather not have. And if we do it the normal way, we're leaving a lot of that to whatever the vendor is doing, maybe a lot of it under the hood. We like to get away from that to try to get at more reproducible science. So we're going to try to replace that with some open source acquisition that will be the majority of my talk today, and then also open source reconstruction, which I'll touch on as I go. So at the end, we're going to try to remove some of that acquisition, say recon variance, separate that from your intrinsic site or hardware that you have going on. And as part of that, we can avoid things like the dreaded scanner software revision that can change things under the hood, all right? So in this example from ABCD, we're collecting a lot of data at a lot of sites. We're getting phantom data over time. We calculate metrics on that, right? So here I'm just plotting the signal fluctuation and noise ratio collected on GE sites here in red and black, and Siemens sites here in green and blue over time. So we start off the study, we get, whatever relatively stable values for each vendor. But then here in 2018, there was a shift, and that shift was due to a software revision on the GE side that probably changed some things about the RF along the way. So we can try to avoid some of these things that will fight against our harmonization efforts if we can try to have more open, stated up front acquisition parameters. So what are we going to do for our various open source acquisition? Okay, so this has been thought of for a while now. There's a lot of solutions out there, such as Odin, RT-Hawk, GammaStar. Then there's a few that are more kind of on the context-independent site. So we're going to specify things kind of in a open, easy to read text file. So I'm talking here about things like PulseSeq and TOPI. And then due to time constraints today, I'll focus on the one that we're using currently, which is PulseSeq. So the idea here is that we're specifying everything going on in the pulse sequence using PulseSeq. using probably some open source tools to do that I'll touch on. That's going to give us our text file, which is going to be the same text file that we take to a GE site, a Siemens site, your scanner vendor site, to translate into that specific hardware. But doing that open source and stated up front, hopefully that takes care of some of that variability that we see if you were to program that individually on each site. All right, gonna stay high level here, but in general, PulseSeq is gonna take your things happening in your pulse sequence, your RF, your gradients, your readouts. It's gonna turn that into blocks of timing of what's going on, and it's basically just gonna play that out as a sequence in a simple text file. Kind of gets away from the idea of a rigid TR. It's just going to play out a sequence of events. Okay, so being able to separate that kind of logical sequence representation, that lets you kind of give you options about all your other parts that you're doing, right? So I can use MATLAB or Python, I'll mention those, or other open source efforts to design my sequence. And then likewise, to analyze my sequence, to plot it, to simulate it, to worry about safety checks, I can put it into open source tools of my choosing. And then at the end, again, we translate that into each vendor's particular code by using an interpreter or a driver. So again, just an example on the MATLAB side, not going into the details, but this is a simple gradient echo sequence, okay? So again, in MATLAB, you know, engineers like MATLAB. Anyway, we define the properties, we define our objects, we're calculating our delays, and then again, we're generating everything into that sequence of blocks that we're gonna turn into that PulseSeq text file that gets played on the scanner. Since I'm in MATLAB, I can use MATLAB tools. This is a simple one that'll just give me the plot of everything going on my different channels. But then you might say, oh, look, we're talking open science here. MATLAB might not be the most open tool you can use, and I would agree. So of course, we have solutions for this in Python and more open source things as well. So if you were to do something in Python, there's PyPulseSeq, which you can combine with things like Google Colab. So you can do the same sort of sequence definition in Python, right? And then if you're combining that with something like Google Colab, that means you can generate all of this in just a browser and never have to use any local resources. So, and then just continuing on with PyPulseSeq, it's been implemented on the range of vendors in MRI. So right now, your big three, and then a few of the lower field options coming up. So they've gone all the way from 7T down to, you know, really low field. And then they have a number of use cases that could be interesting for your particular application, right? Multi-site studies, DTI, things like that. All right. Okay, so hopefully trying to emphasize the open science aspects here. Again, PulseSeq is an open standard for defining your sequence. Lets you use open source tools such as MATLAB or Python to both design and analyze your sequence. Then you can ask, all right, what about that last step, that interpretation when you're putting it on the particular vendors? All right, so a number of the vendors, particularly the ones that we're used to working with right now, GE and Siemens, and I think United as well, their interpreters are open, right? And then the other ones are either being developed in the community or by the vendors themselves. And to that point, at the recent ISMRM in May, there was a session where all 5 human vendors now stated their support both for the open science, open sequence sort of push, and particularly using PulseSeq on each of the platforms. So, all right. So then you can ask, all right, I've collected my open sequence data. Now I would still like to make images. So of course, you have to, at some point, do the process of getting your raw data and turning it into images. But again, we'd like to do this in an open science way. So just a couple points there, right? So even the raw data format choice could be more shareable, more of an open standard. Okay, so HDF5 is a common data format right now, just in general, but a particular instantiation of that is the ISMRM RD raw data format, which is trying to become the open science version of how you save and share raw data. And along with the data, you also have to worry about your particular header values, right? We'd like all the values that we could possibly get to be able to accurately describe everything you need for reconstruction, everything that went on in the data. And then down the road, when you've formed your images, what you have in your header can impact your reproducibility and your anonymization efforts. And I think that'll be talked about a bit in the next talk. So for the reconstruction itself, turning the raw data into images, I don't have time to get into the details here, but two of the major packages are BART and Gadgetron. BART is the Berkeley Advanced Reconstruction Toolbox. Point is that both of them are very well supported, have large communities. Both of them support the ISMRD format, and I believe both of them have Python options. So, all right, so in my dwindling time, I'm just gonna give you a quick run through our particular project at Michigan to have basically a vendor agnostic functional MRI workflow. All right, so we have a couple of different aspects of this. We have a shimming protocol, we have a quality assurance protocol, but for time, I'll just focus on our PulseSeq supported multiband EPI protocol, all right? So we're styling our multiband EPI after the ABCD protocol. So this is your standard multiband 6, 2.4 isotropic resolution, 800 millisecond TR. We've used PulseSeq to describe this thing, again, as a sequence of blocks. And here we're just using the GE pulse simulator to look at the entire sequence. So just some quick results. You know, if I use the product ABCD sequences, I get images. If I use the PulseSeq vendor agnostic sequence, we get very similar images. If I look at some quality metrics, all right, so now we scanned the subject 4 times, scanned a subject during resting state 4 times at a number of different sites, okay, spanning Siemens and GE. And then we're gonna calculate a metric. This is full width half max, which is just a measure of spatial autocorrelation along each axis. And the point here is that if we plot that for the product in blue and the PulseSeq data in red, the variance of these values for each of these metrics is less with PulseSeq. So as we go along these vendors, we're getting less variance with now our vendor agnostic sequence. All right. And then we can do the standard things with task data. This is an N of 1, so I'm not going to claim anything about it other than, yes, we see activation with PulseSeq as well. We've got a traveling subject study where we're scanning a poor soul at multiple different sites. These are our current collaborators. You could be one as well. We're always looking for more people to try out, more sites to try out. So again, back to that repeated resting state scan on multiple vendors, basically averaging together all the resting state data across the sites for both product and PulseSeq, basically generating our connectivity matrices that we get out of Con. We get very similar results using product and PulseSeq. So at the first takeaway is yes, we're getting very similar results to what you would get if you use the vendor sequence. And then even in the standard deviation, they're still pretty similar. We're getting this higher standard deviation on the product one, but I'm not gonna put down the product sequences just based on that, as it could be just subject variance for some reason. So, but if you want to see our human results about that harmonized vendor agnostic study, please see poster 1937. That's up today and tomorrow. And then finally, I have a few QR codes to throw at you. So we have a PulseSeq project site that has our multiband EPI project on there. We've got a diffusion one. We're happy to host other people's PulseSeq projects. For funding, for people who want to get into this, there's actually a NIH R34 grant that's meant to disseminate things that are coming out of these U24 resources. So our project happens to be one of them, this vendor agnostic fMRI sequence. So if anyone would like to try it out at their institution, this is a possible source of funding. And then finally, again, we have a resource website here that we have things for PIs about how you can possibly put it into your NIH grant, put it into your local IRB application, and then of course resources for the pulse sequence developers who are going to try this out. So we have the sequence creation scripts, we have some image recon scripts, and then we're going to soon have some example data sets up there. All right. And then the feedback one on the bottom is, if you have any questions, you want to get involved. Also, if you're interested in a monthly user group meeting that we're going to start about PulseSeq in neuroimaging. All right, and then I will thank the development team, just acknowledging the two major players here. So Maxim Zaitsev at University of Freiburg maintains PulseSeq overall, and then John Friedrich, again, is our leader at Michigan about all things vendor agnostic. Thank you.